morning, everybody. Welcome to Independence Aviation, the weather seminar for spring weather hazard seminar with Mike Centennial here. As everybody probably knows him, he's the chief meteorologist for Jefferson. We welcome you to IA and our quarterly weather seminars. Let's see. We have a sign-up sheet over here. If you have not signed up, please do so. Put your email and phone number down there. And if you'd like wings credit for this event, please initial it or write wings or something so we know to do that. It has to be the correct email that you have on account for wings, FAA. Secondly, Taylor asked me, he also said if you see the date, disregard the date column on this. That's only for our record keeping when you signed up. He wanted everybody to know that. And then if you'd like to be involved with our radar blips email, we put out once a week or so, I think. Please put your email on there that you'd like that sent to. It's good information for IA, about flying in the local area, and present some stuff there. What else? You doing a raffle list now? Always.
Yeah.
So we have.
I'll go through.
You go through that. You go through that. So donuts, coffee. Certainly, if we appreciate any donations you might want to give toward the donuts and coffee. We have a jar up here. And without further ado, Mike Centennial.
All right. Welcome. Good morning, everybody. How many? This is your first time to a weather seminar here at Independence. Okay, quite a few new people. Well, welcome everybody. For those who've been here before, I have to bore you with this information. My name is Mike Centennial. I have worked as a meteorologist for Jefferson for the past 34 years. Always find it fascinating. We get a BS degree in meteorology. Some of you may find that humorous because we lie sometimes. It's really not our fault, but we can go into that in detail if you want. But I've been an operational meteorologist. I've managed an operational group. Did a lot of programming, product manager, and the last thing you see down here is that when you spend hours and hours of complete boredom chasing storms, where you're out in the middle of nowhere in Kansas and Oklahoma, Texas, and finally you get to see one, you do have some fun and go nuts a little bit when you get that 2 minutes of glory after 12 hours of driving around and sitting in fields waiting for stuff to happen. So you're here today, hopefully to get a better understanding of aviation weather, how that impacts you when you're flying. I like to have a very active participation, so if you ever have a question of anything you see up here, please raise your hand. Let's have a discussion about it. Odds are other people are probably wondering the same thing that you are. Why we're here is because these statistics, unfortunately, have not changed a whole lot over the past 20 to 30 years. And you see that a lot of the accident statistics we have here, about 22% of all aviation accidents involve weather, and unfortunately about a quarter of those that involve weather remain fatal. And that statistic really hasn't changed a whole lot in the last 30 years. And even though there's been great advances in some of the technology that's available to you for weather in the cockpit, people are probably a little more emboldened to make decisions and go into places that they maybe shouldn't be going. But the more you understand about this, hopefully the better decisions that you can make. These are NTSB statistics from 07 to 09 showing kind of the total number of accidents there in the blue and the number of fatal accidents for each type of weather category. So you see winds are the number one cause of weather-related incidents, but not very many are fatal. When you get in things like reduced visibilities, low ceilings, we start getting into more than half of those being fatal. And the reason is we have a lot of VFR pilots who are flying into IMC type conditions. The other interesting thing I find, these are the number of fatal accidents in Colorado during 2000 to 2009. Notice where all the fatalities are. They're all basically on the west side of I-25. As we get into the mountainous terrain, a lot of different things can happen there that don't give you as many outs. So we get out here on the eastern plains, you got a lot more room to maneuver, places to land. We don't have near as many fatalities. So the agenda today, we're going to look at spring weather hazards. This tends to be one of my longer classes, just because spring weather has really all of the hazards you can imagine for aviation. Springtime brings out, we still have winter type icing, snowstorms. We starting to get into severe weather season, thunderstorms. So we have all the kind of hazards you can think of in aviation are really prevalent during the spring months, especially here in the United States. So we're going to have 2 breaks. After each break, I'm going to put up a trivia question. Everybody has a chance to win a aviation weather book from Jepson that was written by my old professor, Peter Luster from San Jose State. And then we're going to look in depth at thunderstorms. We're just starting to kick off thunderstorm season. Not so much here in Colorado, especially kind of east of here in the Midwest and the South. We've had quite a few thunderstorms. Severe season is kicking off, but we're not too far away here in Colorado. I have another break, and then we do the last scenario I always do is a flight scenario. So I pick a sample flight somewhere, kind of representative of the topics that we're looking at, and we go through looking at the weather for that trip. I also want to mention we have a special guest here today. So after the first break, when you come back, Greg Thompson, who is very well known in aviation weather, kind of the father of the ADS weather site, is going to get some feedback from you from a application that he has written for aviation weather. So after we come back from the first break, Greg's going to spend about 15 minutes with you, trying to get some feedback for him to help him with that application. So spring weather, we talk really meteorologically, we talk March 1st to May 31st. Those 3 months are really the spring weather months from a meteorological standpoint. We still have cold air masses, we still get snow. The jet stream is still pretty strong and prevalent, so that's why we get a lot of dynamics involved in severe weather season. Warm and humid air masses are starting to move farther north, so when those cold and warm air masses clash, that's when we get our severe weather, those active cold fronts. And here in Colorado, we know springtime sometimes means that we get a lot of our snow. Not so much this year so far, but last year, especially March and April, were very snowy months here in eastern Colorado. So from a long wave, and what I'll talk about here, long wave climatology. So when we have dips in the jet stream, farther south in the northern hemisphere, we call those long wave upper level troughs. And where those upper level troughs kind of hang out during the spring months are these red lines that you see here. The yellow line represents the polar jet stream, mean position, and the purple line is the subtropical jet stream, which is at a little higher altitude, the mean position of those jet streams during the spring months. So this is about a 30, 40-year climatological look. So we look at where these upper level troughs hang out, and that's where we tend to have kind of more violent weather. Where we have upper level troughs, we have more lift, we have more clouds, more dynamics for the atmosphere to work with. So across the United States, as we talked about earlier, the West Coast still is kind of ending their rainy season, but they still have quite a bit of precipitation in the spring months. The Rocky Mountain region can have our higher snow months, not so much this year. And severe weather season is kicking off in the Midwest here. Basically anything east of the Rockies to the Appalachians is where we have a lot of that severe weather. Thunderstorms start kicking off. And the East Coast can still have some of their nor'easters, rainfall, and even a little bit of snowfall in the early spring months. So when we look at hazards in the springtime, obviously number one hazard is thunderstorms. We have frontal and squall line type, which become more prevalent in the spring months. And air mass type really are more prevalent in the summer months. Later in the summer months, the squall line and frontal thunderstorms are more active in the springtime. We still have icing, so we'll look at that, turbulence, and instrument meteorological conditions. So fog, stratus, precipitation can all contribute to those IMC conditions. So we're going to look in more depth at thunderstorms in the second section here, but I'm going to briefly kind of go through a little bit about thunderstorms, about the causes, how they form and that stuff, and then we're going to get into a lot more detail in the second section here. So what is a thunderstorm? Well, it's simply a storm in which there is lightning. It's characterized by lightning and thunder, hail, microburst, potential wind shear, as well as strong up and down drafts within that thunderstorm. When we have severe thunderstorms, that's simply a thunderstorm that has hail that's at least 1 inch in diameter and or wind speeds of 58 miles per hour at the surface. It can also produce funnel clouds and tornadoes. So in severe thunderstorms, we get more turbulence, more icing, stronger up and down drafts, we have microbursts, wind shear, rotating mesocyclones, like we see in the bottom picture down here, and potential funnel clouds and tornadoes. So obviously things you want to stay away from as a pilot.
Mike,
Yes?
why 58 miles an hour?
Why not 57?
I'm not going to try to defend what numbers were chosen for various things. It just happens to be. It's really knots that they categorize it by, and it happens to be 58 miles per hour. So it's 50 knots.
So maybe 50 knots.
Exactly. It's what was chosen. It used to be 3/4 of an inch of hail, and now it's 1 inch for the damaging part. So for thunderstorm types, we talked earlier, we got two different types, the frontal or convergence lines. So those are associated with some type of front or squall line. They move along with that lift that's being produced by the front or the squall line, and they really can develop and sustain any time of day and night. So as long as you have that lift and you have enough instability in the atmosphere, they can actually maintain during nighttime hours, unlike kind of thermally driven thunderstorms that die down after the sun sets. Most severe thunderstorms are of this type that are associated with that convergence line or front, and they're much more prevalent in the spring and then again in the fall months. Air mass or thermal thunderstorms are caused by the sun heating the earth, that air being lifted. They typically develop in the afternoon, they die down after sunset, they're slower moving and typically don't become severe, even though they can in some cases, and they're much more prevalent in the summer months.
That's what I think.
So if you take one thing away from the class today for thunderstorms, it's this slide right here. You need 3 ingredients in order for thunderstorms to develop and sustain. So we have to have lift in the atmosphere. We have to have air that's going upward. You have to have enough moisture to form a cloud, because you can have lift, but if you don't have moisture, you're not going to form a cloud. And the last one, which is kind of the hardest one for pilots to understand, is the instability in the atmosphere. So we're going to talk more about what that means. But if you have lift and you have moisture, you form a cloud, and then the instability is really what causes that cloud to continue to grow and become a thunderstorm. So how do we get these various things? So lift, the most common form of lift is by heating. Sun heats the earth, that air is lighter, it rises, and we get lift. Also in Colorado, we have these things called mountains. Anytime you have a sloping surface, the sun heats that sloping surface faster than it does a flat surface. So when we have sloping surfaces, we actually get more lift off that. And that's why when you have mountainous regions, thunderstorms tend to kick off faster. Convergence. So we can also have fronts or squall lines, air being lifted along that convergence line. Things like sea breeze fronts in Florida, intersecting outflow boundaries. So we have clusters of thunderstorms. They have outflow boundaries. Where those outflow boundaries intersect, we get new lift regions. Dry lines like we have in West Texas, and surface troughs, and then orographic flow. Anytime you have air flowing upward along a mountain surface, that also creates a lift. So here in Colorado, we have a couple different ways of getting that lift.
What's a dry line?
Good question. Fed right into the next slide here. So this map actually shows where this dashed red line is here. That's denoted as a dry line. And what happens is on the west side of that dry line, we have much drier air, and we typically have flow from the southwest. These typically form in West Texas out here. It's the most common area for a dry line. On the east side of this dry line, we have much more humid air. So we have dew points typically in the 50s or 60s on the east side of that dry line. Dew points probably in the 20s or 30s on the west side of that. Southwest winds, we have southerly or southeasterly winds, so that creates a convergence line along that dry line. There's really, when you fly through it, you're not going to notice a whole lot except for that wind shift. And if you had temperature and moisture information, you can see a discrepancy as you fly through there. But thunderstorms tend to form along that boundary because we have that convergence. So we also have to have enough moisture in the air for once we lift it, for that moisture to condense and form a cloud. So typically when we're talking thunderstorms, we want dew points above the 50 to 60 degree Fahrenheit range. That produces enough moisture typically to get that storm going. When we get west of here on the western US, we have much drier air, so it's harder to have enough of that moisture to get things kicked off here.
So, quick question, and I'm sorry for belaboring the point.
No.
So, the lifting has to do with the competing air masses as opposed to one sliding in or over the other,
It's
right?
mostly convergence.
Yeah.
So southwest winds on one side, southeast on the other, so you have convergence of the winds. And that typically tends to create the lift. And then we have enough moisture out on this side to then create the clouds.
Thanks.
So the last part, the hardest part to really kind of grasp and get your head around is this instability part. So when we talk about instability in the atmosphere, we talk about the lapse rate, temperature lapse rate. So the decrease of temperature with height in the atmosphere is known as the lapse rate. When we have a lapse rate greater than either the dry or moist adiabatic lapse rate, which is 3 degrees C per 1,000 feet for the dry adiabatic lapse rate, 2 degrees C per 1,000 for the moist adiabatic lapse rate. If we have a lapse rate that is less than that, we have buoyancy. What happens is the air gets lifted, it then becomes warmer than the surrounding air around it, and it continues to rise. The surface heating helps to destabilize the lower portion of the atmosphere, and cooling aloft, things like an upper level trough, tend to promote destabilization in the upper atmosphere. So in this diagram down here, this dashed red line is the dry adiabatic lapse rate. 3 degrees C per 1,000 feet, temperature is decreasing as we go up in the atmosphere. So vertically, we're going up in the atmosphere here. What happens on any given day is the temperature profile does different things. So in this bottom layer, the actual temperature lapse rate is decreasing much faster than this dry adiabatic lapse rate. That makes this portion of the atmosphere unstable. When that temperature is equal to the dry adiabatic lapse rate, we call that neutral. But in reality, in the atmosphere, that is actually a somewhat unstable portion of the atmosphere. If we have lapse rates equal to the adiabatic lapse rate, what do we call when the temperature increases with height? What's that called? Yeah, an inversion. That is an incredibly stable portion of the atmosphere. When temperature increases with height, it's very stable. It tends to put a cap on everything, so that things trying to get lifted through this inversion have a very hard time continuing to get lifted. And then when we have the temperature that's decreasing at a rate greater than the dry adiabatic lapse rate, we consider that also a stable portion of the atmosphere. So we need this unstable portion to promote buoyancy in the atmosphere. So in a severe thunderstorm environment, we need the same three ingredients, and we tend to have stronger instability. We also have vertical wind shear. So the lapse rates tend to be greater in a severe thunderstorm environment, and we need this vertical wind shear to create the rotation of the storm itself. So we tend to have southeasterly, southerly flow at the surface, and it kind of changes to southwesterly or westerly flow aloft. And that creates that vertical wind shear environment that help these start to begin to rotate. So we also have different stages of thunderstorm development. So we can have a dry thermal stage where we only have one ingredient, and that's lift. So anybody that's flown in the desert southwest, no clouds in the sky, but you can get bumped around a whole bunch. And that's because of these thermals that are simply warm air that's being lifted, but there's not enough moisture in the air for a cloud to condense. So we have lift here. We have the cumulus stage, we have lift and we have moisture. So we formed a cloud, and in a developing cumulus cloud, the one thing to know as a pilot, that all the air is rising in that cloud. So if you were to fly through that developing cumulus cloud, there would only be lift going on in that cloud. And if you get to the top of this cloud, where it's rising faster, that's where you're going to get bumped around the most. So when you're flying in the tops of these developing cumulus, you can get bumped around pretty good up there. Cumulonimbus stage, we now have a mature thunderstorm. We have lift, we have moisture, we now have instability where this developing cumulus, if it were to, an inversion were to be at a higher level, this cloud would just all of a sudden collapse. We wouldn't be able to grow anymore because the air up here, the air in the cloud, would now be colder than the environment and would sink back down. when we have an unstable environment, this cloud now, if it's getting into this area, it's warmer than the surrounding air. It continues to grow, and we get this mature cumulonimbus thunderstorm. Reaches up to the anvil, which is the tropopause typically. Tops of the anvil is right at the tropopause, and the cloud kind of spreads out. If we have enough energy in this, we can actually get an overshooting top to actually punch through the tropopause. But in the cumulonimbus stage, we have a lot of different motions, a lot of vertical motions, upward as well as downward, and we have outflow, we have gust fronts, we have all sorts of things that are very hazardous to aviation. We get to the supercell stage, we have all the lift, moisture, instability, we add in vertical wind shear, and we get this rotating storm. Again, both of these very hazardous to be around in aviation, not only for general aviation, light planes, but also we get into commercial aircraft, it becomes a very hazardous situation. So we all know thunderstorms involve lightning. Lightning is simply the electrical discharge between oppositely charged areas, either within the cloud and the ground, or within two clouds. So the particles become charged due to the updraft and downdrafts, and typically the presence of ice crystals help those charged particles. For a pilot, the important thing to know that only 25% of total lightning is cloud to ground. So what that means, if you're flying below the base of the cloud, you're in an area where only 25% of lightning occurs. If you're flying above the cloud base, that's an area where 75% of lightning occurs. Cloud to cloud, within cloud, cloud to air, etc. But you don't want to be in that part in between. So thunder is simply, it's a result of lightning. Lightning is basically this superheated column of air, and thunder is the adiabatic expansion of that superheated air around the lightning bolt itself, which can have temperatures up to 50,000 degrees Fahrenheit, much hotter than the surface of the sun. So that adiabatic expansion moves away at the speed of sound, about 762 miles per hour at sea level. To determine how far away you are when you see a flash of lightning and you hear thunder, for every 5 seconds is about 1 mile, approximately. It's a good kind of rule of thumb to go by. So, if you count 10 seconds, you're 2 miles away, and typically when lightning is farther than 5 to 10 miles away, it's hard to actually then hear the thunder. So another hazard with thunderstorms is hail. So as cumulonimbus clouds begin to grow, a portion of that cloud is going to be above the freezing level. So when the particles are being transported upward in that cloud, they freeze, they get heavy, and they drop back down. They begin to melt as they get down below the freezing level, and they get recirculated. And that's how hail grows within a cloud. So the stronger the updraft in a cloud, the larger that hail can get, because it circulates many different times before it actually then gets heavy enough and falls out of the cloud. And just know that just because you have a clear slot between the anvil and the cloud doesn't mean you're in clear air. Hail can actually get ejected out of the anvil and fall down through that area. So you can't actually encounter hail, sometimes in clear air, far away from the cloud. And we all know hail can do bad things to airplanes. This happened to be, it was a 727 at nighttime flying over Iowa. It was around at 35,000 feet. Didn't really see what was going on and went through a pretty good hail shaft. And you can see the damage to the nose cone, the windscreen, quite a bit of damage in the aircraft itself. So I used to fly around an airplane with a, instead of metal, it had cloth as its screen. Didn't do so well in hail. So on the climatology side, this is the average number of days per year that there are thunderstorms. So you can see the legend over there on the left-hand side. So you can see where we have more moisture, we tend to have more thunderstorms. So southeastern United States, Florida kind of takes the cake for more than 90 days per year with thunderstorms, because we get this sea breeze effect, air coming off the Atlantic, air coming off the Gulf of Mexico, and it converges over the Florida peninsula there. So we get quite a few thunderstorms. Colorado, we're generally in that 30 to 50 or 50 to 70 days per year, obviously mostly from the months of April through about September, October, and then southeastern Colorado tends to be the more prevalent area for those thunderstorms. And we see on the west coast, where we have a bunch of moisture, big ocean out there, we don't have many thunderstorms. Why is that?
No lifting.
So no, you can have lift out there as well. We got mountains, we got terrain.
Instability then?
There you go. Yeah, so it's a really stable environment off the west coast. So we have moisture, we can have lift, but we don't have the instability that cloud going. So a little tornado climatology. We've all heard of Tornado Alley. This is indeed Tornado Alley, right here through the Midwest, from Texas up through Oklahoma, Kansas. So I get to go storm chasing every year, have lots of fun. But unfortunately, that's where the damaging type tornadoes are. And to a lot of people's surprise, Florida actually has a fair number of tornadoes. But they tend to be in the EF0, the EF1 category. They're not real intense tornadoes, but they still get quite a few of them. Interesting graph down here at the bottom. So if you look at this graph, we have the number of fatalities in green, which is in general gone down, which is a good thing. We have better systems to warn people when tornadoes are forming and coming. But the number of tornadoes has gone up a lot. Why do you think that is?
Better reporting.
Yeah, so we have better detection mechanisms to, we have radar now that can detect tornadoes, and we have a lot more people living in rural areas that we didn't have before. So we're getting more eyes on tornadoes and stuff. So each year is a little bit different from a tornado standpoint. Last year was a pretty light year for tornadoes. This year we started off with quite a few already in January and February. Okay, so another hazard in the spring months is icing. So icing occurs when we have super cooled water droplets. So that's water in a state that is below freezing but still liquid. So water is one of these bizarre substances that can remain in these different states. Normal temperature ranges for icing, we have clear icing, which is the most hazardous form of icing. It's the heaviest, usually in the 0 to -5 Celsius range. Rime ice, -10 to 20, and mixed -5 to 15. Rime ice being the lightest form of ice, it's mostly ice crystals that are formed together. Clear ice obviously being the most dangerous to encounter. So icing can occur in temps down to -40 C in convective type clouds, but it's usually below -20. It gets a lot more sketchy as far as actually getting into icing conditions. Severe icing is associated with super large droplets. So those are droplets typically greater than 40 microns in diameter. And then 12% of all aviation accidents involve icing. So where is the icing environment? So anytime we have frontal systems, we have lift, we have clouds, usually temperatures below freezing. That creates that icing environment. Anytime we have overrunning Gulf of Mexico, think warm, moist air coming up from the Gulf, overruns a stationary or a warm front, and on the cold side of that front tends to be good icing conditions. Anywhere we have freezing rain, rising over mountains, so here in Colorado, winter type months, we get quite a bit of icing. Anywhere you have thunderstorms, and then on the ground, always got to make sure you clean off frost, snow, and if there's any freezing rain or drizzle, probably not a good day to go flying. So we can see here the icing risk over here on the left-hand side. So we have cumulus clouds, stratiform clouds, and the high probability is in those temperature ranges. So you can see in cumulus clouds, 0 to -20 is your highest probability of icing. Stratiform at 0 to -15. And then here are the icing types again with the temperature ranges. So this is just an example of a kind of icing environment where we have a warm front, we have warmer air, rain's falling through, it's freezing when it touches the ground here, and then temperature ranges, we have colder air up above, and we get on the upper altitude side of that front. And at the surface, this is what it would look like. So here I was talking about this air coming up from the Gulf of Mexico. Warmer air, we have this stationary front. We get on the cold side of that stationary front, this is the area in here that would be much more prone to the icing environment for aviation. So it tends to be along cold fronts and on the cold side of stationary and warm fronts. This was an actual surface map taken. This red dot here represents the ATR incident in Roselawn, Indiana. The aircraft was in a holding pattern trying to get into Chicago. You can see all the icing reports that were occurring. So you look at this frontal system, so we have icing reports along the front, and then a lot of them to the north of that warm front. And that's where the aircraft was holding. In moderate icing, aircraft became iced up, wasn't capable of really shedding the ice, and ended up crashing there. So again, icing climatology, when we look at this graph was created by taking radiosonde weather balloon soundings and looking at the potential for temperatures below freezing and cloud conditions during the basically winter months from November to March or April. And this is a percentage of soundings that had these icing conditions. So if you look in areas where you have a lot of moisture, clouds, and cooler temperatures, the Great Lakes is kind of that best area across the United States for icing, the Northeast, as well as the Pacific Northwest. And again, a lot of clouds, temperatures below freezing, those are icing conditions. So thunderstorms can obviously induce icing anytime you get above altitudes where temperatures are below freezing. We have an abundance of these super large droplets. Cooling in the downdraft can cause a lowering of that freezing level, even though you look at the freezing level map. We actually get cooler temperatures as we get those downdrafts. And you can get all kinds of icing in thunderstorms. So turbulence, another hazard that's still prevalent in the springtime months. Talk first about low-level turbulence, that's below 18,000 feet. Mostly due to mechanical turbulence, strong surface winds around rough terrain. Thermal turbulence, so those are updrafts induced by surface heating. And then low-level wind shear, things like around frontal systems where you have a convergence of winds, thunderstorm wind shear, as well as here in Colorado, we still get a little bit of mountain wave turbulence in our early springtime months out here. So this is a diagram here talking about mountain wave turbulence. So we have some mountain out here. We have flow that's coming from the left of the screen to the right. As it goes over that ridge or mountainous terrain, it causes the downstream wave pattern. So here you notice, here's the wave pattern downstream. Each wave gets subsequently less intense as you get further away from the mountain. So the greatest turbulence tends to be from the crest of the mountain range to this first wave downstream. That's where we tend to have the strongest low-level turbulence from a mountain wave situation. So everyone flying out here knows you fly closer to the foothills, the front range, we tend to get stronger turbulence when we have that mountain wave situation occurring. Here's the scale. So you can see these waves as we go out about 20 miles from the mountain range, it tends to get much less intense. So when you're trying to land here in a mountain wave situation, flying farther east at higher altitude, coming back down, is typically the best way to avoid some of that turbulence. So picture from NCAR, looking to the west out here, we have that cap cloud that hangs out along the crest of the mountain range. Then we have downsloping wind on the east side of that, dries everything out, lenticular clouds at higher altitudes, and we can get these rotor clouds that actually occur at or below about mountaintop level. So anytime you see a rotor type cloud, you know that you have a very intense mountain wave situation occurring. Very strong turbulence that you would want to stay away from. So when we get higher altitudes above 18,000 feet, we're talking upper level turbulence, mostly associated with jet stream type encounters or wind shears associated with the jet stream. We can also have thunderstorm induced turbulence at higher altitudes, and mountain wave turbulence can occur at higher altitudes above mountaintop level as well. So this is a schematic here of the jet stream. So think of the jet stream being that black dot going directly into the screen. So that's the core of the jet stream. The blue zone here represents the strongest turbulence associated with that jet stream. So when we get near the tropopause, above the jet stream, we can get a fair amount of turbulence. And in this baroclinic zone here, where you have the strongest gradient of winds, is where the strongest turbulence would be associated typically with the jet stream. So if you're flying at higher altitudes, typically this would be the warm side of the jet stream. That would be the cold side of the jet stream. The warm side tends to have less wind shear. Colder side, we tend to have stronger wind shears. And turbulence generally we think of just being uncomfortable, a little bit annoying, but in some cases, turbulence has caused some problems with aircraft. So the picture on the upper left there is a B-52. That was being flown by Boeing Flight Test Group out of Wichita. They were flying around New Mexico at about 500 feet, checking out how the aircraft would handle low-level encounters, because they were looking at, hey, if we have to go into Russia, we have to fly at very low levels, how's the aircraft going to handle? So they were flying along around 500 feet over New Mexico, and they started getting bumped around pretty good. So crew thought, well, we'll go at higher altitude. We'll go up 14,000 feet, and we'll find some smoother air. They happened to be flying just in the lee of the Sangre de Cristo Mountains at that point. Right at mountaintop level, they encountered severe turbulence associated with a very strong mountain wave situation, and it ripped, as you can see, the back end of the aircraft, the tail and the rudder basically off. They were able to actually land the aircraft back at Blytheville Air Force Base in Arkansas. They wanted to go back to Wichita. The crosswinds were enough that it caused a problem. When you don't have a rudder, really hard to land in a crosswind. So they went to Blytheville. Winds were right along the runway. They were able to come down and land. This over here, this is a 3-engine variant of a DC-8 aircraft. They were flying at around 31,000 feet over Colorado near Evergreen. Very strong mountain wave situation, and 18 feet of the left wing and one engine actually got ripped off the airplane. And it was able to come back and land safely at Stapleton Airport.
Dropped off near your home, right?
I haven't found it yet. I still look for it. So as you can see here, a lot of different vertical motions in thunderstorms, so we can get a lot of different types of turbulence, both at the ground level with the gust front, as well as within the cloud itself, and even above the cloud. In some cases, when we have the anvil and overshooting tops, it can actually cause its own mountain wave situation downstream of a thunderstorm. So even aircraft flying at very high levels near the tropopause have to be worried about turbulence associated with thunderstorms. So lastly, we'll talk IMC, instrument meteorological conditions for our spring hazards. So that's ceilings greater than 1,000 and or visibility less than 3 miles. Fog can cause it, low clouds, coastal stratus if you're flying on the west coast, haze, mist, smoke, precipitation, all sorts of things can cause these limitations to visibility and or ceiling height. And if we're a VFR pilot, those are conditions that we want to stay out of. So fog is typically a low-level, ground-based phenomenon. It occurs when the air above the surface is cooled from the ground itself, creates that condensation just above it. So we tend to have moist ground or body of water. Cool, calm, and clear nights are the best conditions for fog to form. We want a stable environment, not unstable, so we want stability in that lower portion of the atmosphere. And that typically has occurred by high pressure at the surface and an upper level ridge aloft. And then valleys, lakes, and coastal areas are most common for that type of fog. This is a high-res satellite image. This is the Central Valley of California. So this is prime conditions, wintertime. You see snow along the Sierra Nevadas up here still. And anytime we have enough moisture on the ground, again, those calm, clear nights, we get this fog that forms, very dense fog in the Central Valley of California. Used to have to drive through that going skiing in the wintertime. Not a lot of fun. So coastal stratus occurs when we have cool ocean waters that cool warmer air above it from the cooler water itself. When we tend to have onshore flow, that stratus moves inland. When we have offshore flow, that stratus stays off the coast. So it moves inland overnight, retreats to the coastline during the day, and it kind of pulses back and forth. This is mostly a summertime phenomenon along the west coast, all the way from British Columbia all the way down to Baja, California. And the marine layer is defined from the surface to the base of the marine inversion, which is the top of the stratus deck. It averages depth about 1,000 to 2,000 feet above the height of the ground, and it increases, it goes a little bit higher if an upper level trough is approaching, gets compressed when an upper level ridge occurs. But if you want to practice your IFR flying, this is a great place and location to do it.
One thing to consider.
Pretty much every day.
With ground fog, many times you can see down through it. If you're in it, you can't see anything.
Yeah, good point. It's shallow enough that you can sometimes actually see down right through it, but if you're in it, slant line, it's much harder. The visibility is greatly reduced. I've actually been in that ground fog situation. You go over an overpass and you're actually above it. It's that shallow. It can be about 10 feet high sometimes. But if you're driving in it, it's horrible. So this is a visible satellite image of coastal stratus here. Coast of California. You can see that stratus right up against the coast. It comes inland in some of the valleys. That's the Salinas Valley there.
On the last slide, you said that the ceilings in coastal fog are usually 100 to 800 feet. Why is it? Why doesn't that just go down to the water or to the ground?
It needs enough basically condensation level to form, so that the stratus deck tends to form. It takes a while for the ocean to cool the air above it, and it doesn't condense until usually that height. It's somewhere between a couple hundred feet and about 1,000 feet. Yeah, so you can, a lot of times you can fly underneath it, but you can't penetrate it unless you got some instruments to maneuver with. And this is a typical upper air sound, this weather sounding of a stratus situation. So the red line is the temperature, the green line is the dew point. So you notice down near the surface, they're very close together. So you have those clouds. And then once we reach this, what's called the marine inversion, temperature increases rapidly and air dries out rapidly. So it's a really sharp break. When you punch through the stratus deck, you're up into clear, really warm air. I used to have to climb up on Mount Sutro Tower to take observations there, and as you're climbing up through the tower, you would actually climb through this layer. So it'd be cold, windy, foggy, and then all of a sudden you reach this point and it's just beautifully clear, and the temperature sometimes would rise 20 to 30 degrees Fahrenheit within a couple hundred feet. So it warms up very quickly. And then other places are fronts that get a lot of IMC. Schematic of a cold front and a warm front. So the cold front, notice, has a steeper slope. Because of that steeper slope, we tend to get more vertical convective type clouds along the cold front. This is the slope of a warm front. We tend to get more layered clouds. So instead of the convective vertical clouds, we tend to get more layered type clouds. But you're going to fly through a warm front, you're going to have to fly through that a much longer period of time and distance to get through the clouds versus flying through a cold front. And our IMC climatology, number of days per year with IMC type conditions. Notice when we follow the moisture, a lot of moisture on the East Coast and the Gulf Coast, a lot more days of IMC, as well as the Pacific Northwest. They've had a pretty rough year up there. Been to Seattle quite a few times. They've had, I think it's 3 actual complete sunny days since October this year. So it's been a rough year for them. But a lot, and then you see the coast of California, there are a lot of IMC during the summer type months. The old saying that the coldest winter ever spent was a summer in San Francisco can be absolutely true. So we look at annual precipitation, gauge over here on the left-hand side. When we have that more moisture available, we have more precipitation, so the eastern part of the United States gives a lot more precipitation annually. Western part tends to be much drier, except in certain cases, like California this year had a whole bunch of precipitation. I saw Paradise, California was up in the foothills, has had 85 inches of rain so far this year. So lots of rainfall,
Hanging on to it.
but not so much the last couple of years. Okay, so we're at our first break. This will be a fun situation if you're out storm chasing to see stuff like this. We're going to have our first chance at winning a prize. So if you don't have any scratch paper, there's some up here. You guys want to pass that around back there? Go ahead and write down your best guess at this question. Put them up on the computer here, and then we'll pick a winner out of the correct responses to win a weather book when we come back from break. But in 2016, which month had the highest number of severe weather reports? So 1 out of 12 chance. You can probably eliminate a couple of months out of that. But write the month that you choose down. Yes, this is CONUS. Anyway, not a lot of severe reports usually in Alaska and Hawaii, but this is the total of the CONUS. Which month had the highest number of severe weather reports? Put your name on it, the month, set it down, and then we'll take about a 10-minute break here, come back, pick the winner, and then Greg's going to show a demo of his application.